All right, Chem 4, we are back and we are wrapping up chapter 4 today. Chapter 5 on radioactivity. And again, we have a lot of information here that'll be on your homework. And then one particular type of information, the half-life, that is going to be on the exam. So I'll make sure to re-emphasize it when we come to that. But for now, let's go ahead and learn a few things about radiation. One concern that you should have about radiation is how to measure it. And there's a variety of different ways that you can measure radiation that we're going to explore here in this part of the chapter. So the first thing is one way that you can measure a radioactive source is using what's called a Geiger counter. Now, this is in like every movie, anything that involves like a radioactive source. So like, I think like Ghostbusters, there's like basically a Geiger counter analog for measuring ghosts for them. But just like anytime you're looking for something that's radioactive, you have this long cone source here that basically, if it hits radiation, electrons are then hit this detector in the middle, and that creates a current that the meter then clicks or registers. So you start hearing like clicks, or there's different ways that it can audibilize that. But this is kind of a famous way of measuring individual decays of radiation. And then the closer it is to the radioactive source, the more radiation hits it, the faster it moves. So there's several different ways of measuring radiation, as I mentioned, and we'll mention a few of them here. So a Curie, for example, is the number of decays that occur in 1 second for 1 gram. So that for 1 gram of radium is 3.7 times 10 to the 10th disintegrations per second. That's just one way of measuring like how many decays are going on. And that is particularly for the radium itself. So 1 Curie is 3.7 times 10 to the 10th disintegrations per second, or decays. You can think of it in terms of decays as well. The becquerel is the SI unit for radiation activity, and that is simply 1 disintegration per second. So this is a very small unit. As you can see, the Curie, which was used before the becquerel, is a massive unit, 3.7 times 10 to the 10th. So of course we're going to have like a large number of becquerels when we compare the same type of radioactivity. Now there's 2 other ones, which is RAD and REM. So RAD is radiation absorbed dose, which measures the amount of radiation that is absorbed by a gram of material. And then in particular for the body, the REM is the radiation equivalent of humans, which particularly measures the biological effects that different kinds of radiation have. So in a hospital setting, like the REM is what's most important, because specific types of radiation, as we mentioned, are different, and so they have different effects on human bodies. Okay, so let's look at the REM real quick. So for REM, that's going to measure basically the following. For alpha particles in the exterior environment don't really affect the body, because alpha particles can be stopped just by the layer of skin, the dead skin on the outside. So alpha particles aren't a problem until they get into your body. Now, once they get into your body, they can cause extensive damage to your tissue. And this is why alpha emitters can be used as deadly poisons, like polonium has been used as a poison before. That's because if you take polonium in, it emits alpha particles that then cause your organs to shut down. There's also gamma radiation, for example. Gamma rays are damaging, and that's because they can hit anywhere in the body, because they can travel through any amount of shielding that you have, save a very thick lead or concrete shield. So to determine a REM dosage, what they do is they take the absorbed dose and multiply by a factor to account for biological damage. For beta and gamma radiation, the factor is 1. For high energy protons or neutrons, the factor is 10. And for alpha particles, the factor is 20. Basically, think of it like this. If it gets inside your body, an alpha particle is like a truck. So it's just going to like ram right through. for the high energy protons and neutrons, they're extremely damaging too, but they're more like a car. So maybe this is like a cement truck. This is a car, and then the beta and gamma radiation might be like a bicycle or something like that. It's still going to hurt if it hits you, but it might be more survivable than the truck. So that's not going to be on the test, but I just wanted to kind of like explore that, because maybe some of you are going to work in units that involve radio medicine, and so it's important just to hear these words first from me, and then you'll learn about it on the job. So if you're going to work in a radio medicine laboratory, you're going to have this dosimeter on your clothing at all time. And this dosimeter is going to measure the amount of radiation exposure that you get from your X-rays, your gamma rays, or beta particles, because those are the ones that can penetrate the skin and the lab coat that you're wearing. So usually this is going to measure in terms of millirems. So 1 rem is, of course, 1,000 millirems. And 1 sievert is 100 rems. I know that's confusing, but I'm not going to be asking you to do these conversions. I just want to like expose you to this information before you actually do you have some kind of problem. So for different different types of radiation have different measurement units. The activity, it can be measured by the Curie or the becquerel. The absorbed dose is either the rad or the gray, and then the biological damage is the rem or the sievert. Okay, so where are you exposed to radiation? Well, the truth is radiation is all around us in the modern world. On average, each person in the United States is exposed to 3.6 millisieverts of radiation each year. So exposure to your radiation can occur in the buildings where you live and work, the food and water that you eat, and of course, the air that you breathe. Naturally occurring radiation occurs in the form of potassium-40, which can decay in the body. That's naturally occurring. You also get a dose of cosmic radiation from the sun, including X-rays and gamma rays. And then there can also be medical sources of radiation, including X-rays, mammograms, and a variety of sources that we're going to talk about at the end of this chapter. So here's an example of the radiation that you can receive by a person per day. So like, where do you get your, sorry, this is annual, not per day. This is annual radiation. So just to give you an idea, like you get it from birth, so from the ground. There's naturally occurring isotopes that are radioactive, and they're emitting radiation, just a small amount, 0.2 millisieverts. Air, water, and food, so this is what you're breathing, eating, drinking, 0.3 millisieverts. Cosmic rays from the sun, 0.4. And then wood, concrete, and brick can all include the radioactive isotopes as well. So it's all around you, but it's very small. So don't worry too much about that. For example, when you go into the to get an X-ray for your chest or for your teeth, you're going to take a dose of about 0.2 millisieverts each, and that's pretty safe. That's fine. And a mammogram takes 0.4 millisieverts. Now, as we go down here, we're getting more and more of this radiation, as we see here. So a hip X-ray goes up to 0.6 millisieverts, for the spine, 0.7, and then if you need to take an X-ray of your GI tract, that doses you with 2 millisieverts. And the reason for that is simply you're dosing your very soft tissue in the GI tract with X-rays, which it's more sensitive than the other places that we were looking at. Other sources include, you get some from nuclear power plants. Your television has some radioactive isotopes. Air travel as well. So if you travel in air a lot, so if you fly a lot, there's you're farther up in the atmosphere, there's less air molecules absorbing the cosmic rays from the sun. So you get more radiation up there. And then finally, radon. This is not really a factor here, but in some places in I think in particular, Iowa is pretty bad about this. You build a basement into the ground, and in the ground, there's naturally occurring sources of lead, and that lead is radioactive. Now, that's not necessarily a problem on its own because lead is solid, right? but this lead decays into radon. And radon, if you look on the periodic table, it's in the noble gases. It's a noble gas and it's radioactive. So that's a problem because if you're down in that basement and you're inhaling radon all day, well, that's putting a significant amount of radioactivity into your body. So that's a real problem in particular places in the Midwest, I say. And it has to be in the basement because you get it from the ground. So not really a problem here. You probably don't have a basement, and you probably are not. I don't think there's like a big radon source in California. Okay, so let's see here. What do we want to talk about with radiation signal? Okay, here we go. So if you're exposed to less than 0.25 sieverts, you wouldn't detect it necessarily. If your whole body gets 1 sievert, it really affects your immune system. So it's going to temporarily decrease your number of white cells, which can decrease your immune response. If you get greater than 1 sievert, however, that's when you're on the verge of radiation sickness, nausea, which includes nausea, vomiting, fatigue, and severely reduced immunity. The basic math of the sievert is that if the average, so if a group of people is exposed to 5 sieverts each, it's expected to kill half the people that receive that dose with radiation sickness. What's really interesting is different species have different tolerances for radiation. So this is why, like, the famous cockroach that survives the apocalypse exists, is because insects have a very high tolerance for radiation. And it's about 200 times the amount that a human can tolerate. But a dog actually has less tolerance for radiation. Okay, so this is an important introduction here. The concept of LD50. I'll put that on the exam because I think that is important. Basically, the amount of radiation that would kill 50% of the population is what's called the LD50, or the lethal dose for 1/2 of the population. And this LD50 applies across a variety of concepts. There's an LD50 for arsenic, for lead, for water. There's an LD50. Anything that's poisonous will have an LD50. Radiation in particular has this 5 sievert LD50. Okay, now we mentioned already that one of the sources of radiation that you can get is from your food. And, that sounds scary, perhaps. It's like, why are we putting radiation into our food? Well, with the food system in the United States, there's a big problem with bacterial infection. Specifically, you probably heard of salmonella infections, listeria infections, and E. coli infections in foods, just given the food system that we have in the United States. So what food shippers do is, once they get the food, they'll dose it with a small amount of radiation from cobalt-60 or cesium-137 to treat foods. What they do is they take cobalt pellets, they place them in stainless steel tubes and arranged in racks, and the food passes through the racks with the gamma rays then passing through the food and killing the bacteria that's on it. This is an example of the type of benefits that you get from that, where the strawberries that you see on the right side have been irradiated, and this on the left were not irradiated, and this is after 2 weeks. So no spoilage on the radiated ones, and significant spoilage on the ones on the left. Yeah, so right now, tomatoes, blueberries, strawberries, mushrooms are all irradiated. Okay, yeah, I'm not going to require you to memorize this. You will need to know it for the homework. So you might as well, let's pause here and answer the question. Match each property with what is measuring it. So it's like activity. Which of these measures the activity of radiation? Which one measures the absorbed dose? And then which one measures the biological damage? So we can go ahead and pause. And we are back. Let's go ahead and take a look at here. So activity is measured by the becquerel, or the curie. The absorbed dose is measured by the millirad. And then finally, the biological damage is measured by the millirem or the sievert. So both of those count. Okay, here we go. This is the next part that's on the exam, which is the ability to understand what a half-life is. Half-lives are really important in medicine, not only because of radioactivity, but also it's a useful way to describe the way that the body excretes certain substances, and in particular, medicines. So when we're talking about half-lives, in this chapter, we're going to talk about it in terms of radioactive substances decay. But I want you to also think of it in terms of when I administer a medicine to a patient, they're going to start with this dose in their blood, and then the half-life means that after every so often, they're going to reduce it by half of what's left in the body, basically. So let's go ahead. We're going to talk about it in terms of radioisotopes, but then we'll try to steer it towards medicine after that. Okay, so here's the way radiation works, and this can be a little bit mind-bending because it's not how we think of things, but this is the way that radiation occurs. The half-life of a radioisotope is constant, and it is specifically the time that it takes for the radiation level to decrease by 1/2 of its original value. So if you start with 20 milligrams of iodine-131, if after one half-life, you'll be left with 10 milligrams. After 2 half-lives, so twice the amount of time, you're left with 5.0 milligrams. In other words, half of the second number. If you wait another half-life, it reduces by half again to 2.5 milligrams. So this half-life represents a certain amount of time that can be measured. And each time this time passes, you're left with half of what you started with. So you have 20, one half-life goes to 10. After a second half-life, it goes to 5. And then after a third half-life, it goes to 2.5. And this gives you an idea on the decay curve here. Now, for iodine-131, we see that it has a half-life of 8 days. So after every 8 days, the amount of radiation from the iodine-131 decays in half. So if we start again with 20 milligrams, ends up at 10 after 8 days. After 16 days, it halves again to 5 milligrams. After 24 days, it halves again to 2.5 milligrams, halves again after 32 days to 1.25, and then from there to 0.675 and lower. Okay, so here are some half-lives of some commonly occurring isotopes that we see. So carbon-14, that's used in radiocarbon dating, has a half-life of about 5,730 years. Potassium-40 has a half-life of about 1.3 times 10 to the 9th years, so a huge amount of a hugely long half-life beyond our imagination, really. Same thing with uranium-238, 4.5 times 10 to the 9th years is older than the age of the universe. So it takes a long time for that to decay. Strontium-90 is at 38.1 years, and radium-226 is at 1,600 years. For medicine, it's important to use isotopes that have a very short half-life. So things like carbon-11, which has a 20-minute half-life and emits a positron, and chromium-51, which has a half-life of just 28 days and has gamma emission. Wrapping up our table of medical isotopes, iodine-131 has a half-life of 8 days, oxygen-15 is 2.0 minutes, iron-59, 44 days, radon-222, 3.8 days, and then technetium-99M, that we talked about in the last lecture, has a half-life of 6.0 hours. So again, these are useful depending on what you're looking at. You don't need to memorize any of this, but I just want to kind of point out here that the shorter the half-life, the more useful it is in a medical setting. Okay, so let's look at how we can use half-life for a radioisotope and how we can answer this question. So here we go. The radioisotope of strontium-90 has a half-life of 38.1 years. If a sample contains 36 milligrams of strontium-90, how many milligrams will remain after 114.3 years? So when we see this type of question, what we want to ask ourselves is, okay, we know the initial amount, that's 36 milligrams. How many half-lives did it have to go through to get to the final amount here at 114.3 years? Well, the way that we can determine that is by taking the total amount of time, 114.3 years, and divide it by the half-life, which is 38.1 years. That's going to give us the number of half-lives. So if one half-life is 38.1 years, then all we have to do is take 114.3 years, multiply it by one half-life times divided by 38.1 years. That gives us the answer 3 half-lives. So we know it's been through 3 half-lives after 114.3 years. Well, then we just do a little bit of easy math, right? We're starting with 36 milligrams. After the first half-life, that cuts in half to 18 milligrams. The second half-life then cuts it in again to 9.0 milligrams. And then finally, we cut it in half a final time for the third half-life to 4.5 milligrams. So the answer for the question is 4.5 milligrams of strontium-90 remain. Okay, let's do another example of this, but this is the sample exercise. So I want you to try to think this through first. So let's go ahead and I'll walk you through the question, and then we'll walk you through the answer after you give it a try. So sample exercise number 6, iodine 123, which is used in the treatment of thyroid, brain, and prostate cancer, has a half-life of 13.2 hours. How much of a 64 milligram sample of iodine 123 is left after 26.4 hours? So go ahead, pause the video, try to answer this question, and then we'll look at it ourselves together when you come back. So go ahead, pause. Okay, we're back. So the question here is basically, how many half-lives does iodine 123 go through in 26.4 hours? Well, we're given in the problem here that it has a half-life of 13.2 hours. So if we take the fact that 26.4 hours divided by 13.2 hours, we know that we've gone through 2 half-lives. So from there, it's a simple, all we have to do is basically multiply it by half twice. So we take 64 after one half-life, turns into 32. After a second half-life, it turns into 16. So that tells us the answer is 16 milligrams of iodine 123 remain. Okay, so that's the type of math that you'll have to do for this chapter. I hope that's relatively straightforward, but definitely ask me any questions if you have any that pop up in the comments below. Okay, so one thing that is really interesting about radioisotopes is that they can actually be used to determine archaeological ages. So you can use carbon-14 dating, as it's known, to determine the age of bones, let's say. So the way that it works basically is this. Carbon-14 comes from the upper atmosphere. So nitrogen-14 absorbs high-energy neutrons from the sun, and it decays into carbon-14. Okay, so that produces carbon-14 in the upper atmosphere. Now that filters its way down into the lower atmosphere at a regular rate, and then plants uptake that carbon, that carbon in the form of carbon dioxide, turn it into sugars, et cetera, et cetera. Then we eat those sugars, and we're taking in carbon-14 all the time. But here's the thing. Once the plant dies, it's no longer taking in CO2, so the total amount of carbon-14 stops at that point. And from there, because it's a radioisotope, it slowly decays over time. In fact, it has a half-life of 5,730 years. So you can use carbon-14 dating to date anything that's biological from within the last, I think it's 50,000 years or so. You can get a good idea of what the time that the plant or animal died, right? Because animals get all of their carbon from other animals, but also from plants. So eventually we end up with the same amount of carbon-14 as long as we're alive. Okay, now we're going to go through just very briefly radioactive applications in medicine, because radioisotopes can be used to diagnose or treat different diseases. So you don't have to memorize these, but I think these show up a little bit on the homework, and then they're just important to know in case you are interested in applying radiomedicine, for example. Okay, it's important when you're doing this that you use radioisotopes that have short half-lives, like what we mentioned before. We need to make sure that the cells in the body, don't take up too many of these radioactive atoms, because they're going to emit radiation, and they're going to they could damage an organ or more. So for example, gold-198 locates in the liver, and it's used to help treat abdominal carcinoma. So because it goes to the abdomen, any liver cancer cells are going to take it up more than other cells. And so you're going to use that radiation to kill the cancer. Note all of these that have that we're talking about here have half-lives of like minutes to days. They're all very short, no years, weeks, or months here. It's all within a matter of days that it will be out of the system. We have lots of different applications here. We don't have to look at each of them necessarily, but for example, iodine 131 can be used to image the thyroid. Let's see here. Anything else that's interesting? Yeah, just this gives you an idea of where it can be used for, like bone cancer, breast cancer, prostate cancer, leukemia, pancreatic cancer, liver cancer. Each organ and each tissue takes up different atoms more readily. So you want to choose the correct radioactive atom to locate in the correct spot. Okay, so here, learning check. It's not on your sheet, but just which of the following are likely to be used in nuclear medicine? So this is an example of a question I could definitely ask on the test. So would you use potassium 40? Would you use potassium 42? This should be potassium 42 here, not 421. And then iodine 131. What would be most likely to be used? Well, the ones with short half-lives would be used, right? The potassium 42 or the iodine 131. Okay, so how does imaging work with radioisotopes? Well, what you do is you dose the patient with the radioisotope, and then you have a scanner, which is just a detector. You can think of it like a camera, basically, for whatever emitted radiation is used. The scanner is going to slowly move across the body in the region that contains the organ that the radioisotope is going to locate. The radiation tech will determine the level and location of radioactivity, and then by measuring, by basically imaging the scans from the gamma rays and whatever else happens to be used in this case. So you could also measure the the electrons that are produced or emitted, and that allows you to take a look at the organ or tissue that you happen to be looking at. So this is what a thyroid looks like after it's been treated with iodine 131. So it shows up here in the scan really effectively. Now, another type of therapy is what's known as positron emission therapy or tomography, positron emission tomography or PET scans. In this case, the patient is dosed with a positron emitter that has a short half-life. And then you put that in a substance that the body's going to take up, like glucose. And then it closely tracks with blood flow and brain function. So a PET scan most famously is used on the brain because you get a lot of detail about regions of the brain that are active based on the amount of positrons that are being emitted, where the blood is flowing to, and where that oxygen and glucose is being used up. On the left, this shows normal brain. On the right, you see a brain that's been affected by Alzheimer's disease. So you can see that Alzheimer's disease seems to be changing the flow of blood in the brain, which presumably changes neurological activity. Yeah, so the main way that you do this is you have positron emitters like carbon-11, oxygen-15, nitrogen-13, and fluorine-18. These positrons combine with electrons, and as I mentioned, positrons are the antiparticle of electrons. So when they hit each other, they actually annihilate each other and produce gamma rays that then the detectors will scan. Now, there's also a CT scan, which is what's called a computed tomography scan. And this is basically where you use a bunch of X-ray beams at whichever layer of the tissue or whatever organ it is that you're looking at. And you can do like a cross section, for example. That's what we're looking at here of the brain. And based on the densities of the tissues and fluids in the organ, you can show like different densities, and you can see abnormal tissues in the scan. So, like for example, we can see this big tumor in a patient's brain from the CT scan. Now, MRIs, which are probably the most common form of scan, it just stands for magnetic resonance imaging. You don't involve X-ray radiation, and this is the least invasive imaging method that's used. And what you do is basically you apply a strong magnetic field to a person, and as it turns out, hydrogen atoms, when they are in a magnetic field, they either spin up or spin down. And based on how you're shooting it with radiation, just in the form of radio waves, you can actually flip it from going up to going down. So you can then see where that's being absorbed and where it's not being absorbed. And that can give you a good idea of things like blood flow, and just giving a good image of the organ that you're looking at. Okay, finally, we're going to wrap it up by talking about nuclear fission and fusion, which is not going to be really part of our, not going to be on the test, but it's interesting, and a lot of people are interested in it. So I just want to, say a few words about it. And of course, if you have any other questions about it, just let me know. So in the early 1900s and starting in the 1930s, a lot of scientists were working on radiation, and they noticed a few things. One is that for certain substances, if you took a, let's just point out the uranium-235 in particular. If you take a uranium-235 and you hit it with a neutron, it becomes unstable at uranium-236. It becomes unstable and then it decays. Now, when it decays, it does two things. Number one, the atom splits, undergoes a process called fission. So just splitting. And when it splits, it produces 3 neutrons. Now, what happens with these 3 neutrons? What if they each hit 3 uranium nuclei? Well, those are going to split too, and that's going to produce 9. And then from there, it would be 27, 80, 81, et cetera, et cetera. It just keeps going and keeps going and forms a chain reaction. And this could be used for an atomic bomb, is what they were thinking at the time. So yeah, this nuclear fission is just, I guess it's exactly what I said. You take a nucleus and you bombard it with a proton or a neutron. And then what's going to happen is it splits into smaller atoms. For uranium-235, that can produce a chain reaction because the neutrons that are emitted then can hit more uranium-235 and produce more splitting. Again, I'm not going to ask you to balance these equations. Now, one thing that happens is if you added up all the mass of the products, krypton, barium, and the 3 neutrons, it turns out that the product mass is actually less than the starting mass for the uranium-235 and the neutron. So what happened to the missing mass? It's a very small amount of mass that's missing, but it's truly gone. Well, as it turns out, this validates the energy mass relationship that was originally proposed and determined by Albert Einstein, this famous equation E equals mc squared. When we do a nuclear reaction, some of the mass is lost and converted to energy. So what does this tell us? Well, it tells us that mass is energy, just somehow bound up in on itself. This is a pretty interesting relationship for sure. Okay, so we already talked about the chain reaction thing. Now the chain reaction is useful when you're trying to do a nuclear reaction for a power plant, because you just control the number and just say, okay, this one's going to produce 1 more, which is going to produce 1 more, produce 1 more, and absorb the extra neutrons. But of course, it's a problem when your control gets out of hand, the chain reaction goes off, and you have a situation like Chernobyl, where the nuclear reactor melts down and then exposes a huge amount of radiation. Yeah, okay. Now, nuclear fusion, on the other hand, is where you take 2 small nuclei and they combine together to form 1 larger nucleus. And this is, for example, what happens in the sun. The sun right now is taking protons, which are hydrogen nuclei, and sticking them together with neutrons to form helium nuclei. And it happens at really, really high temperatures, 100 million degrees Celsius. And it just produces a tremendous amount of energy to do it. So one thinking is like, if we could do fusion on Earth, of course, there'd be a tremendous amount of energy to put in, but the amount of energy we could get out would be very easy. We also wouldn't have problems of radioactive wastes from nuclear fusion. So nuclear fusion has long been looked at as the source of energy of the future. It's just a very difficult technology to get right. Okay, yeah, so nuclear power plants produce electricity. What do I want to say here? Oh, the key thing is you have to hold uranium-235 below what we call critical mass to make sure that you don't have the chain reaction go out of control, so that you can stop it when you need to. It produces a lot of heat, which then boils water, which turns turbines, which turns electrical generators. Yeah, okay. Yeah, you're not required to remember that necessarily. Okay, let's go through this. Okay, we're not going to do that. Okay, all right. Well, that takes us through the end of the chapter. So just these last sample exercises here are not going to be on the test, but you can go through them and look at the definitions if you want. And then here, it's just another point of like balancing equations. So it's just the same type of stuff that we were doing for alpha, beta, and gamma particles. But now this time it could be anything, right? We don't know what this element is. All you have to do is take 1 plus 235 on this side has to equal 137 plus x plus 2 on this side. And that'll determine the mass number. And you do the same thing for the atomic number too. Okay. All right, well, that does it for chapter 5. Again, chapter 5, what we're going to focus on is not nuclear equations, but the definitions of these particles here. And then we're also going to focus on half-life over here for the test. So again, there'll be a practice test up very soon. And I think once you see that, you'll understand what I'm talking about. Until then, let me know if you have any questions in the comments down below. Posting the practice test soon for you. And yeah, let me know if you have any questions. Until then, bye-bye.